Welcome to Pomodoro Joe for Thursday, May 18th, 2023. Today we're looking at LeetCode problem 1557, minimum number of vertices to reach all nodes. This is a medium problem. Given a directed acyclic graph with n vertices numbered from 0 to n-1, and an array edges where edges index I is equal to from to represents a directed edge from node from to node to, find the smallest set of vertices from which all nodes in the graph are reachable. It is guaranteed that a unique solution exists. Notice that you can return the vertices in any order. When they say vertices here, that's the same as the node, I think. All right. Okay, so this one seems really complicated when we first look at it. But before we start coding, let's just take a minute to step back and analyze the situation. So let's take some examples. Let's say we have one node. It's just one. Well, then the answer here, we just return that node. So we return 1. Now what if we have two nodes, 1 and 2? Well, if they're not connected, we have to return both 1 and 2. But what if they are connected? We could have node 1 pointing to node 2. Well, in that case, we just need to return node 1 because node 1 can reach node 2. Or we could have node 2 pointing to node 1. And in that case, we would have to return node 2 because node 2, you can go to node 1. Okay, let's add a third node into this mix. So we could have nodes 1, 2, and 3. Well, if there's no connection between 3 and the other two nodes, we have to return, in this case, both 2 and 3. But if there is a connection, well, now we can ignore node 2 and we can just return node 3 because from node 3 you can get to 2 to 1. So I'm starting to see a little bit of a pattern here. So if we have a node that has something pointing to it, we can just follow the chain up until we find a node that doesn't have anything pointing to it. So for example, if we add a node 4 into the mix, in this case we just have to return node 4 because from node 4 we can reach all the other nodes. But what if node 4 doesn't point to 3? What if we have node 4 pointing to, say, something like node 2 here? All right, if we have something like this. So node 1 is pointed to by node 2, but node 2 is pointed to by both node 3 and node 4. Well, in this case, we don't need to return node 1 because we can get there from node 2. And we don't need to return node 2 because we can get to node 2 from node 3 and node 4. But node 3, well, we can't get to node 3 from anything but node 3. So we have to return node 3. And same thing with node 4. We can't get to node 4 any way other than just starting at node 4. Okay, so now I see the pattern. Any of these nodes, if there's some other node that points to it, we can ignore returning that node because we can always get to that node from whatever node points to it. And if you have multiple nodes that point to it, that's okay. We're already ignoring that node anyway. So we need to look for all the nodes that don't have other nodes that point to that node and return that set of nodes. All right, that's pretty straightforward actually. So with that, we will start. All right, let's put 25 minutes on the Pomodoro timer, and then let's get started. So by doing our analysis of our graph here, we know that we only need to return nodes that don't have other nodes that point to them. Because if they did have a node pointing to them, then we could just return the node that points to that node. And we already know that this is an acyclic graph, so we don't have to worry about cycles. So let's just look for all the nodes that don't have other nodes pointing to them. All right, that's pretty straightforward. So I'm going to have two sets here. I'm going to use set operations to perform this. I'm going to have an all nodes set, and that's just going to be a set of all the nodes in our graph. And then I'm going to have a destination node set, and that is a set of all the nodes that have other nodes pointing to them. And now we just need to go through our list of edges, pulling out all the nodes and all the destination nodes. So let's see, for our edge in edges, actually I'm going to break this out into from and to. So from node and to node in every one of our edges. We can say all nodes will add the from node, and then destination nodes will add the to node. Okay, so now we have two sets, one that contains all of the nodes, and another that contains just the destination nodes. At this point, we can just return the difference between the two sets. So we'll return all nodes minus the destination nodes, because the destination nodes we know we can reach from other nodes. All right, let's see if this works. It seems to work. Let's submit that. And we pass, and we're done. So we beat 39% for runtime and 23% for memory, so not too bad. Let's just jump back and do a couple of optimizations. I don't know if these will actually make it faster, but they seem like they might. All right, so one thing that we can do, we're going through all of our edges and adding these source nodes or from nodes. We could have the same node pointing to multiple nodes, which means we'll be adding that same node multiple times. So rather than putting our source nodes into our all nodes group here, let's just go through our range n, add that source node one time, and then we won't have duplicate adds for every source node. So let's try that. I'll just call it node in, no, I can't call it n. So I'll use the same terminology here for the from node in range n. So this will go from 0 to n minus 1. Then we can just move this into this other loop. Now we will be going through a new loop, so this might actually be slower. Kind of depends on whether or not this loop will be faster than having duplicate adds. Seems to still work. Let's go. And that actually doesn't save us anything. We do better with the original solution. So let's go back to our original solution. Now, one thing I'm not doing is I'm not actually turning this into a list. This will probably take longer. This is actually the more appropriate answer, but it'll probably take longer. Yeah, not any faster. In fact, it is slower. All right, let's try one more solution here. Instead of keeping sets, this is, I think, the cleaner solution. Let's actually go through and build up a list. So that might be a little bit faster, but we'll see. Okay, so let's have some list of nodes. So we'll call this nodes. And we'll set it equal to 0 times n. So now we have essentially one entry in our nodes list for every node in our graph. Now for every, well, this will kind of be the same thing we had before, from and to in edges. Or I could call it source and destination. Here, I'm going to call it source and destination. Mix it up a bit. For every source node to destination node in our edges, well, our source node, we can do nothing. We don't need to worry about that. But for our destination node, we can flag, oh, maybe I'm going to flip this around. It's 1 for every node. All right, so I'm going to flip this around a little bit and start the nodes with 1 as their initial value. That way, when we go through later, we can pull out just the nodes that haven't been flipped to a 0. So we're going to flip all the destination nodes to 0, meaning don't include them in our final output. So we just say nodes at destination equals 0. So by the time we get done with this for loop, all of our nodes in our nodes list will be either 1 or 0. All the nodes that don't have any nodes pointing to them will still have a 1 as their value. All the destination nodes will now have a 0 as their value. So we just have to build up a new list of nodes that only includes nodes with 1 as their value. So in this solution, we'll go through our entire list of edges. Any node that is a destination node, we're going to flip its value in this nodes array to 0. Then we'll go through that node array, but we'll enumerate it because the node is actually the index, and the value will be whether or not to include it in our result. If we have an inclusion, then we will include that node. and then we return our results. Okay, that works. Let's see if this is faster than our set solution. And it is. It's significantly faster, in fact. So we beat 81% for runtime and 16% for memory. So this solution is a little bit messier in terms of implementation. I actually prefer the set solution better, but it is faster. And there are things that we can do, of course, to clean this up. We could go through and basically build our list in place in our result, make it a one-liner, but I'm just going to leave it here. 81% is pretty good. All right, well, I think that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.